All right, so we move on to 11N. Any questions on 11E? Actually, when you read it, you will come up with more questions. Please do, and please ask the next time. 11N. So 11N introduced the 4 new things. First is MIMO. And we already talked about MIMO. How many antennas you put and how many antennas you receive. And so given N by M colon K, where N is the transmitting antenna, M is the receiving antenna, then K are the streams. How many streams you send. Okay? And basically what happens is these are the streams inside the receiver. I mean, inside, you might have, see here it shows here it shows 3 antennas, but only 2 streams inside. So K is the number of parallel radio chains inside, which is less than the number of antennas. There is no point in having more than the number of antennas. So these 2 antennas are combined in this case, and there are many ways to combine. We said take the best of them, take the average of them, take the minimum, whatever. I mean, there are many ways. So this is the thing. So you want to 2 by 2 colon 2, or 2 by 3 colon 2, or 4 by 4 colon 4. So diversity, more received antenna than the number of streams. That is diversity. Beam forming is focused in one particular direction. And MIMO power save, which means that you don't have to have all the antennas on all the time. So now previously the station could go to sleep. Now the station could be awake, but the antennas could go to sleep. So that is what 11N did. Keep going more, or actually not 4 is 13. And it does frame aggregation. So you can put multiple frames inside a frame. Now this is different than frame bursting. Frame bursting is basically at the physical layer. This is more like IP segmentation and the assembly stuff. You know, you can take multiple frames and put into one frame. So it looks like one frame. If you have very small frames, then you can put many of them into one frame. Frame aggregation. Lower FEC overhead. So instead of 5/6, they use 3/4. Now 3/4 and 5/6, what is the difference? 3/4 would be 9 by 12, and 5/6 is 10 by 12. Reduced guard interval. So there is guard. We saw the guard in the frequency domain, but there is also guard in the time domain. When we send something, we stop for some time. Okay, so that the frames don't run into each other. And so that is called guard interval. So 400 nanosecond instead of 800 nanosecond. Reduced interframe spacing, 2 microseconds. So by the time 11N came, which is 10 years after the technology started, now we are shaving off everywhere, trying to get every last bit we can get. And so reduced interframe spacing, 2 microseconds instead of 10 microseconds. Green field mode, which means that don't implement ABG. Everybody has to speak N. That is difficult to do. So there is a mode there, but I don't think anybody uses that. Yeah.
Is the guard interval between symbols?
Guard interval is between symbols. Yeah. Yeah, between symbols, yeah.
Excuse me, that makes lower because for each 5 we have 1 extra, but before we had for every 3 bits we had 1 extra. So 5 to 6 is less than. I mean,
so I am doing calculation wrong, huh? 10 by 12.
Because no, because for each 5 bits we have only 1 extra, but before for each 3 bits we had 1 extra. So it's lower.
Oh, okay, the lower is better.
Yes.
9, okay. So 10 by 12 is better than 9 by 12. Yeah, I was just thinking in the wrong direction. You're right. Thank you. Everybody got that idea? So the point is, 5 by the higher fraction is better. Higher fraction. If I do 1 after 1, that is better in terms of performance. Although error rate. So there are 2 performance: throughput performance and the error performance, right? So 5 by 6 is better because we don't have too much overhead. Only 1 bit overhead. That is 20%. Every 5 bit we add 1 bit, right? There we had for every 3 bits we added 1, right? So the 33% overhead, something like that. So So 5 by 6 is better than 3 by 4. Good. Actually, so I was just comparing the fractions. The lower fractions is better. So 5 by 6, sorry, whatever. You understand. The lower number of extra bit is better for the throughput, not so good for the error. All right, so let's say greenfield mode. Everybody understood greenfield mode? The next thing was dual band. So N works in both 2.4 and 5.8. Space-time block code. And when you get an 11N device, which, today if you buy, I think you are going to get minimum, lowest, cheapest thing is 11N. You will have both bands, and you can decide whether you want to use both or one, and which one. Okay. So for example, at my home, I have not started 5.6. I mean, I first started 5.6, and then I turned off. Basically, and I don't know why, but basically this is an arbitrary decision. You can have different networks on those two too. I mean, then it asks me what is the name of your 5.6 network and what is the name of your 2.4. You could give the same name, you could give different names, things like that. Dual band. Space-time block code, and this requires explanation, STBC. And I think there might be a slide right after this. Channel bonding. Channel bonding means that you don't have to use 20 megahertz. You can use 40 megahertz, 20 plus 20, 2 channels together, 3 channels together. And this is now continuous. So now by the time we get to AC and other things, we are not using 20 megahertz. We are using this big, this big, this big. More subcarriers. Now they used 42 plus 4 instead of 48 plus 4 with 20 megahertz. So they used 4 more. So now here is what they are doing. They are taking 4 less pilot or something, 4 more for data. So again, this is good for throughput, but bad for error correction. And so 108 plus 6 with 40 megahertz. So now if you have 4 streams, each with 64 QAM, with 5 by 6 FEC, and 40 megahertz with 400 nanoseconds. Okay. Now you multiply each of these. So this one, 400 nanoseconds is not very easy to multiply, but 400 nanoseconds instead of 800 nanoseconds, you have to see what is the symbol time, and this will come out as a fraction. So you put that fraction here. Okay. And then multiply all these numbers. Instead of 64 QAM, you put how many bits per hertz, and you will see that now you can get 600 megabits per second instead of previous 55 or 54 or something. All right. Now guard interval. Question was guard interval. Guard interval is between the symbols. You have a data symbol, guard interval, data symbol, guard interval, data symbol, guard interval. So basically, guard interval should be 4 times the multipath delay spread. This is a rule of thumb. So if you are in a small room, the delay cannot be that large. The delay spread cannot be that large, and therefore, you can have a smaller guard interval. You can go to your thing and say 400 nanosecond. On the other hand, you're in a big hall or in a big area, like, near the library outside. Then, there are lots of reflection points. The delay spread could be large. There you would not want to change to 400 nanosecond guard interval. So initial 11.8 design assume 200 nanosecond delay spread and assume 800 nanosecond guard interval plus 3200 nanosecond. This is the number I am missing. So if you have 3200 nanosecond data and 800 nanosecond, you have 20% overhead, right? And most indoor environments are 50 to 75. So if both sides agree, means receiver and transmitter agree, then 800 can be used in 11N. And so 400 plus 3200 will give you 11% overhead as opposed to twice that much. So the overhead would be, instead of 1.22, it will be 1.11. I mean, you can multiplier here. For 400 nanosecond, you get 11% less overhead, whatever. So that is how you calculate.